Our next speaker is Maria Gorinova. She's going to talk about SlicStan, optimizing probabilistic programs using information flow analysis. Right?
Hi, thanks very much for the introduction. So many of you were probably at the talk about Stan earlier this morning, or you've heard about Stan before. It's one of these probabilistic programming languages that is available for use at the moment. It has growing user community, and yeah, it's pretty great. And today I'm going to talk about SlicStan, which is what I called a blockless version of Stan that uses static analysis in order to optimize the program for probabilistic inference. I really hope that by the end of this talk, I'll convince you to see probabilistic programming languages as more than just a convenient interface for probabilistic modeling, but also to see them as a powerful tool that can be used to help inference. Right, so I will start with hopefully a recap of what a Stan program is. So Stan is, a Stan program consists of a sequence of blocks, up to 7 blocks, which are optional, but have to appear in certain order, and different sort of things go in different blocks. And where you put variables changes what happens with inference and how optimal it is, and so on. So in this particular case, this is like a very simple example where we have some data y, and we say that the parameters are mu and sigma, and then here we specify the priors on mu and sigma and the likelihood of data by saying that it's a Gaussian with mean mu and variance sigma, sorry, standard deviation. Then we can also derive the variance as the square of sigma. Now, you might be wondering, what are these blocks? I mean, they're a bit peculiar, aren't they? It's not a usual thing in programming to have these sort of blocks. So why are they there? Especially given that some complications may arise. For example, here we have to declare y quite far from where we give the likelihood on y, right? We also, it's a bit difficult to reason about Stan programs as a composition of other Stan programs. Like, how do we put one Stan program with another Stan program together? And probably most of all parameters need to be declared in the parameters block, which means that we can't declare new parameters in user-defined functions. So yeah, why are the blocks there? Why do they matter, and how do we decide where to put our statement? Well, I think the answer to this is actually in the inference algorithm Stan uses for inference. So Stan uses Hamiltonian Monte Carlo, or HMC, which is an MCMC algorithm. It does inference by sampling a collection of samples from the posterior distribution. And how does it work? So it uses the gradient to make things, to make inference work better. So imagine that the posterior distribution we want to sample from is, really the negative block of it, is a surface. So here the valley is an area of high density, and this bit here is an area of low density. Then we put a particle on this surface, which is, imagine that the position of this particle is like the sample, the current sample, and we just kick it. We give it some momentum, and it starts moving. We simulate this physical system, and we stop after a while, and this is our new sample. The position of the particle is now our new sample. Now, of course, we can't really make a perfect simulation there. We have to discretize time and have all these intermediate steps, which we call leapfrogs, that sort of, are approximation for this simulation. And really, here is where the blocks of Stan go. So we need to somehow explain what part of our model goes as a pre-processing step. So before we start all this process of sampling, what part of our model will go into the very expensive simulation that happens here, where on every step we need to recompute things like the gradient of the target distribution, and what will go as a post-processing after we obtained a new sample. Right, and now what does SlicStan do? Well, SlicStan is basically Stan, but without all these blocks. Yeah, it just figures it out somehow, and I'll explain how. The only thing we have to say is what the data is, but we have to do it. You see that we can do this in any order here. We're not constrained anymore. We can have a more generative story where we firstly declare our parameters, and then we say how the data was generated from them, for example. And how does SlicStan work? Well, it uses information flow and information flow analysis to figure out what sort of block each variable should belong to. And what does that mean? Well, information flow is very simply, it's the transfer of information between two variables. So here we have the information flowing from X to Y, but here we also have information flow because depending on what the value of X is, Y can be 0 or 1. So in both cases, we have the information flowing from X to Y. Information flow and information flow analysis is used in the security community for cases where we want our system consists of some data that may be, say, of higher priority over lower priority or secrecy. And we want to disallow higher priority, higher secrecy data to flow into lower secrecy data. So imagine we have two levels, two secrecy levels. One is public and one is secret. Now, every variable in our program is either public or secret. All of data is either public or secret. And we want to allow things like a secret variable S depending on a public variable P, because why not? Secret information can depend on public one. But we want to disallow the other way to happen. So we don't want flow from secret to public, neither a direct one like here or indirect one like here. And how does that relate to Stan? Well, if we go back to the blocks, as I said, so this is now a full, full 6 blocks without the 7th one, which is functions, of a Stan program. And we identified that we can, because they have to appear in order, and every Stan block can only access things that are defined inside of the Stan block or previously. That means that information in this program flows from the top to the bottom. And we identified 3 information flow levels. So the first one is the data level, where we define constants, we define data that we model, and so on. And then in the middle we have, and this is basically our pre-processing step. I will explain that again in a bit. And then we have the expensive bit of our program, which is the model level, where we define our priors and likelihood and so on, and our parameters. And then at the end we have the generated quantities. So these are quantities that our posterior doesn't depend on, and they're just generated out of whatever we have previously, which could be data or parameters. And now the key idea behind SlicStan is to develop a type system that basically imposes constraints on the levels that variables can have, and figures out all the possible roles that a variable can have during inference based on these constraints. So the constraints would be something like, obviously, if a variable is declared as data, it needs to be of level data, but also if x equals full of y, then the level of x needs to be greater or equal to the level of y, and so on. So a bunch of things like that. But now, of course, these are not unique. So I said, find all possible roles. There are a bunch of constraints. We resolve the constraints, and there are many sort of different levels that a variable can take. So what do we do? How do we choose? Well, remember the particle flowing and so on. Basically, some bits of this computation are more expensive than others. And it turns out, and here is the compulsory table, as mentioned previously, although mine doesn't contain results. So it turns out that the blocks that are associated with the data level are executed only once. That's the pre-processing. That's whatever we can do before we even start inference. And then the blocks that are associated with the model level, this is the expensive bit. This is what we need on every leapfrog step. We need to recompute things, and most of all, recompute the gradient of the target distribution on every leapfrog step, which is quite expensive. And finally, the generated quantities, because our posterior distribution doesn't depend on them, they're just like generated out of whatever samples we got from the posterior. These are executed, this is the post-processing. This is executed only once per sample rather than per leapfrog. So to recap this, we have a bunch of constraints that are enforced by a type system, by information flow type system that has 3 levels, data, model, and GenCont. We resolve these constraints and obtain certain number of possibilities for each variable. And then based on this, we choose the most optimal one, like based on this performance ordering here. And now we can take a SlicStan program like this, which we only annotate what the data we output from the outside world is. We then infer the best possible levels for each of the variables. And after a little bit of transformations of this program, such as reordering, or maybe we need to do some static and aerobic of functions and stuff like that, we can shred this and shred each statement into the respective block of Stan, and we translate to Stan. And this is not only convenient because now we don't have to think about where we should declare our variables and our statements and so on, and what should go where, but also we can have user-defined functions. And some of you might be familiar with this example. This is the news funnel example, which is famous for the fact that some of the variables in the posterior, in the posterior or the distribution we sample from, are very strongly non-linearly dependent, so it's difficult to sample from this distribution. But if we reparameterize the model, and if we instead instead sample these variables that are standard normal and shift and scale x and y, we actually make our inference problem easier. So in Stan, we have to do this manually for each variable we want to transform, while in SlicStan, we can have a user-defined function that declares this new parameter, the standard parameter, and scales and shift to obtain the original one. And I think I've been talking very fast. Yeah, sorry about that. Yeah, to recap, this talk was about SlicStan, which uses static analysis to figure out how to optimize a program for probabilistic inference. And if you're interested, there is this page from a previous workshop that has a bit more information. And also, if you're interested in the more technical details, as well as semantics, the formal semantics of Stan and SlicStan, there will be a technical paper on that coming out soon. And if you're interested, ask me for details. Finally, maybe like what the big message that I want to send with this talk is, which some of you might think it's like a little bit out there. But I think it's really important to not only think of probabilistic programming languages as some sort of nice, convenient interface to probabilistic modeling, which certainly they are, right? But there can be so much more. And we should really try to formalize them and to think about how we can use them in order to help inference. Because, come on, let's face it, inference is so hard that we need all the help we can get to solve it. That's all. Thanks very much.
So we have time for questions. All the way in the back.
Hi, thank you. I like this main message. So, just to continue this direction, so what do you think about the role of standard compiled optimization? So how much can, or do you actually do additional optimization on the program aside from information flow analysis? The last example you showed seems like you also do some additional.
Which example? This one?
Yeah, so please repeat the question.
Okay, so the question is...
Like function inlining, right?
Sorry?
It seems like there is some function inlining going on in there, right? So I was just wondering how much space there is for more involved static program analysis and even optimizations like the compilers for the nodes.
Okay, so the question is, if I understand correctly, is what kind of other static static analysis we can do, mostly standard static analysis that's used in normal programming and so on. And I think the answer to this is all sorts of. There is nothing that stops us to. So in SlicStan, we don't do it. This is this is a research language. It's a prototype. It's mainly a proof of concept, but nothing stops us of doing variable elimination and stuff like that. So other, standard static analysis techniques. But I was talking more about the fact that I think we should think of other sort of static analysis techniques that apply to probabilistic programming in general and to the fact that it can help inference.
All right, let's thank the speaker again.